Ever wonder how we design the powerful computer chips in your phone or create brand new medicines from scratch? Well, the answer is kind of wild. It's hidden in the quantum realm, a world that seems to operate on a completely different set of rules. Today, we're going to pull back the curtain on the brilliant shortcuts that let us calculate the seemingly impossible.
You know, the math behind the quantum world is famously, terrifyingly complex. But here's the little secret. Scientists almost never solve the full equations from scratch. Instead, they use these incredibly clever mental models and approximations, these elegant workarounds that get them to the right answer without the impossible effort. And today, we're going to learn exactly what they are.
Okay, so let's dive right in. Our story actually kicks off more than 100 years ago. And it doesn't start with some complicated theory, but with a simple, everyday observation that completely baffled the greatest minds of the time.
We've all seen this, right? Think about a blacksmith's forge or the filament in an old-school light bulb. As you pump in more heat, the color of that glow changes. It seems totally straightforward, but hiding inside that simple glow was a deep, deep mystery.
Now, physicists being physicists, they gave this phenomenon a pretty fancy name, blackbody radiation. And all they wanted to do was come up with a formula that could predict the exact color and brightness of the light an object would give off at any temperature. Sounds reasonable enough, right?
But this is where things got really, really weird. When they tried to use the established, trusted laws of physics, the rules that had worked for centuries, their calculations went completely off the rails. The math predicted that a glowing piece of metal should be blasting out a blinding, infinite amount of energy, mostly as ultraviolet light, which, is just impossible.
This wasn't just some small miscalculation. This failure was so spectacular, so profound, it earned a very dramatic name, the ultraviolet catastrophe. It was a huge, blinking neon sign that the old rules of physics were fundamentally broken. Something deep about how reality worked was just missing.
So when you have a crisis this big, you need a really bold new idea to fix it. And the solution that finally emerged wasn't just a minor adjustment, it was a complete reinvention of how we thought about energy itself. A physicist named Max Planck came up with an idea that was, well, totally out there for the time. He suggested that maybe energy isn't like a smooth, continuous river. Maybe instead it comes in tiny individual packets he called quanta. Think about a guitar string. It can't just vibrate any way it wants. It can only vibrate at specific, distinct frequencies. Planck said energy works the exact same way. And with that one weird rule, the math was instantly fixed. It perfectly predicted the glow. And just like that, boom, quantum physics was born.
Okay, so Planck's wild idea gives us these new rules, and they work like a charm. But here's the thing. It also created a brand new, monumental challenge for all the scientists who came after him.
See, these new quantum rules, they'd apply to every single atom. So, if you want to figure out the properties of a material, like the silicon in a computer chip, you'd theoretically have to calculate the interactions between all of its trillions and trillions of atoms, all at once. The scale of that calculation isn't just difficult, it's literally impossible for any computer we have or could ever even imagine building.
So how do we get anything done? How do we design new materials or new drugs? Well, in a way, we cheat. Okay, maybe cheat is the wrong word. We use 3 brilliant approximations, these clever shortcuts that get us incredibly close to the right answer by simplifying the whole mess.
All right, so what are these magic tricks? They basically boil down to this: freeze, repeat, and summarize. These are the 3 core strategies, so let's break them down one by one using some simple analogies to see exactly how they work. First up, freeze what barely moves. Imagine you're at a track meet, timing the 100-meter dash. You're laser-focused on the runners. You don't care about the clouds drifting slowly overhead, do you? Of course not. Compared to how fast the runners are moving, the clouds are basically just standing still. Well, believe it or not, that exact same logic applies in the quantum world. Inside an atom, you've got this big, heavy nucleus. That's our slow-moving cloud. And then you have these tiny, super-fast electrons zipping around it. Those are our runners. So scientists use what's called the Born-Oppenheimer approximation. They just freeze the nuclei in place and solve for the behavior of the electrons around them. That one simple trick makes the math so much easier to handle. All right, on to shortcut number 2. Exploit repetition. Imagine you walk into a room with patterned wallpaper. If I asked you to describe it, you wouldn't tell me about every single square inch of the wall, would you? No way. You just show me the one little tile, the single pattern that repeats over and over again. This is precisely how we handle materials like metals or semiconductors. Most of them are crystals, which means their atoms are arranged in a perfectly repeating 3D pattern. They are literally nature's wallpaper. And thanks to a really powerful rule called Bloch's theorem, instead of calculating trillions of atoms, we only need to solve the physics for one tiny repeating box called a unit cell. A problem that was impossible becomes something we can actually do.
Okay, last one. Shortcut number 3 is all about the big picture. Summarize, don't micromanage. Think about a city planner. To figure out where to build a new subway line, they don't need to track the GPS location of every single person in the city. That would be insane. They just look at the overall population density, where the crowds tend to be. Well, the same logic works for atoms. Instead of tracking the mind-bogglingly complex dance of every single electron, scientists just calculate the overall electron density. And it turns out that summary contains almost all the important information. It's genius.
So those 3 ideas, freezing the slow parts, using repetition, and summarizing the crowd, they're not just clever tricks. They are the foundation of modern material science. And what's really cool is they let us tap into some of the absolute weirdest parts of the quantum world to build some truly incredible technology.
So let's talk about one of the most famous and bizarre quantum effects of all. It's called tunneling. Imagine you throw a tennis ball against a solid wall. It's always going to bounce back. It's never, ever going to just phase through the wall and appear on the other side. But in the quantum realm, a particle can. So why does this happen? It's because every particle has a wave function, which you can think of as a wave of probability. It describes all the places the particle might be. And that wave doesn't just hit a barrier and stop cold. A tiny part of it actually leaks through to the other side. This means there's a small but very real probability that the particle will just pop into existence on the other side of a barrier it should never have been able to cross. It's like a ghost walking through a wall.
Now, this isn't just some abstract, weird idea. We actually use this. The scanning tunneling microscope works by bringing an impossibly sharp needle just a fraction of an inch above a surface. And then a tiny electric current of electrons does the impossible. It tunnels across that gap, a gap they shouldn't be able to cross at all.
Now here's the kicker. The amount of that tunneling current is incredibly sensitive to the exact distance. So as the tip scans across the material, the tiny changes in that current build a map so detailed it actually reveals the individual bumps and valleys of the atoms themselves. We are literally seeing atoms one by one, all thanks to a quantum impossibility. So there you have it. We went from a crisis in physics sparked by a simple glowing piece of metal to a set of brilliant shortcuts that let us tame these impossible equations, and finally, to technologies that let us see the actual building blocks of our reality. It really makes you wonder, doesn't it? What other impossibilities are out there just waiting for us to find the right shortcut?